Quantum gravity. Before we tackle this topic, what is gravity? First, let's take a look at the force that we live with every day on Earth.
Gravity. Weak gravitational forces have kept us on our feet for years now and can be explained using these Newtonian equations. However, these equations still have their limits when in the presence of strong gravitational forces or more complex orbits. We weren't really sure how to tackle these until about 1915 with the introduction of Einstein's field equations, and it's where Newtonian mechanics failed that Einstein succeeded. For more examples, just look up.
Einstein managed to prove that his equations of motion and theory of space-time geodesics, that being the curvature of space-time, were more accurate than Newton's equations when calculating the motion of Mercury's orbit. The precession of Mercury's perihelion orbit was around a whole 43 arcseconds ahead of the Newtonian guess, but was predicted exactly by Einstein's groundbreaking new theory. There were other issues with Newtonian gravity that are also taken into account with the new general relativity, notably that they do not work with special relativity. Newton assumed that the gravitational interactions were instantaneous, which would imply that they are faster than the speed of light, which is not correct. Luckily, the new formulations are fully Lorentz invariant, meaning that they are consistent in all inertial frames. So why do we want a quantum version of gravity anyway? Well, assuming that gravity is a fundamental force, it would just make sense. If we now consider the world of quantum mechanics and quantum field theory, we already have quantum representations of the electric and magnetic forces, specifically in quantum electrodynamics or QED, a field theory specific to these two forces. Furthermore, having quantum gravity would bring us one more step closer in the pursuit of a theory of everything, or final theory, or master theory, the pinnacle dream of all physicists that encapsulates all workings of the universe, fully explaining all contained within it. We mentioned earlier how strong gravitational forces break apart previous mechanisms for gravity. Well, it's perhaps a theory of quantum gravity that will help us to understand what occurs in these situations. For example, what happens inside one of these? A black hole. We want to know whether there is space for singularities in our understanding of physics, and what happens to information past the event horizon, a sort of ring of no return. This is referred to as the information loss paradox and is still an active field of research. We hope that being able to find or solve for a theory of quantum gravity will prove fundamental to answering all of these questions. So why haven't we done it already? If you mean to ask why haven't we quantized gravity, well, we have. It just doesn't work with high energies, where most of the previous questions are concerned. In these situations, gravity encounters an issue with quantum field theory, as it is non-renormalizable. That's not to say that it can't be renormalized, but rather it would require an infinite number of what we call counter terms in order to cancel out the UV divergences. Experimentally speaking, infinity is not possible to test for, and so this prevents us from being able to progress in any meaningful way. Perhaps what we need instead is, instead of considering perturbative quantum field theories, we need to look at a non-perturbative quantum field theory approach. But perhaps gravity is not a fundamental force, and it is in fact a consequence of fundamental processes at a microscopic level. In this case, we would refer to gravity as entropic or emergent, meaning it just appears and is not something that should be considered as fundamental.